So I guess we'll start our afternoon session. So I'm happy to introduce and welcome Dr. David Wolpert from the Santa Fe Institute, and he's going to speak to us about the stochastic thermodynamics of computation. Thank you.
Okay, thank you, and thanks for inviting me. This has been really very stimulating. I assume everybody can see my screen. So anyway, a bit of background. Scientists have been interested in the relationship between thermodynamics and computation since at least the 19th century. Maxwell, of course, was concerned with what an information processing demon, we might call it a computing demon, whether they would be able to thwart the second law of thermodynamics. And then, of course, some great progress was made in understanding this relationship and unraveling it here, so to speak, at IBM in the second half of the 20th century. One of the great challenges that people faced, though, in analyzing these issues all the way through the 20th century was at the time, the only tools they really had to use was equilibrium statistical physics, or near equilibrium at most, because that's all that really existed. It turns out, though, fortunately, in the first 2 decades of this century, there's essentially been a revolution in statistical physics. We now have a full-fledged non-equilibrium statistical physics that can consider systems of arbitrary sizes. There's a very, very thriving community right now looking at quantum non-equilibrium statistical physics, as well as nanoscale and so on, where they're arbitrary dynamics. Real computers, almost one of their defining characteristics is that they are very far from equilibrium systems. And so because of this revolution in non-equilibrium statistical physics, we can now actually start to extend all of the insights from the previous millennium into many, many different directions. And that's what I'll be talking about today. In particular, one of the subfields, branches of non-equilibrium statistical physics is called stochastic thermodynamics. So I'll be talking about the stochastic thermodynamics, what you can learn about the energetic properties of computation from stochastic thermodynamics. So I'll begin by just going over some of the relevant aspects of stochastic thermodynamics. One of the great things about it, to be honest, is that it's very, very simple stuff, really, to understand it. So I'll be giving you a primer in about a dozen slides, if that. And then I'll start to illustrate just a few of the ways we can use this to extend our previous understandings of the relationship between computation and thermodynamics. I'll start to begin with, everybody knows, I assume, Kolmogorov complexity. I give you an output bit string, and I want to know the length of the smallest possible length of any inputs to a given Turing machine, universal prefix-free Turing machine, such that it will actually compute that desired output string. There's a natural thermodynamic version of this, where I want to find not as what the smallest length of any input would be, but what is the smallest amount of thermodynamic work that would be required if using a conventional Turing machine architecture, in other words, what is defined in Lee and Vitani or any other of your favorite textbooks saying this is a Turing machine, what would be the minimum amount of work it would need to compute a desired output? And this actually gives you modifications, very, very interesting ones, of Kolmogorov complexity. The next issue that I'll talk about is what some of the thermodynamic properties are of digital circuits. So in particular, I'll look at a loop-free, branch-free circuit that's computing a given Boolean function. It turns out that the minimal thermodynamic work, the generalized Landauer bound, so to speak, for computing a fixed Boolean function depends on the digital circuit you use to compute it. Because of the different topologies of the circuits are going to have different thermodynamic consequences. There's an infinite number of digital circuits that will compute any given desired Boolean function. So there's actually a new optimization problem. Given I want to implement a given Boolean function, what is the digital circuit that will do so while requiring the smallest amount of thermodynamic work? And new kinds of information theoretic quantities come out when you start to wrestle with this optimization problem. It seems to be, though this hasn't been proven, NP hard with very nasty constants in front of the scaling properties. So anyway, just even for such a simple thing as a loop-free digital branch-free circuit, there's all kinds of new rich properties and how this is related to P-poly and things like that. Then, time allowing, I'll try not to squeeze too much in. That's always a hazard when I present talks. But time allowing, these first two presentations are all about what are probably the most common, definitely the most common computers made by human beings, which are synchronous. But certainly some of the ones that human beings use, and all across nature, you have asynchronous computers. The organelles within your cell, those are all different information processors that are communicating with one another in an asynchronous manner. Similarly, the cells in your body, the different people in a social system, what have you. It turns out that there are major thermodynamic consequences to the topology of the communication network coupling a bunch of asynchronous computers. When I restrict you to saying you've got to use a particular topology, then I've actually caused a large increase in the Landauer bound and all kinds of fun things. So anyway, away we go. So stochastic thermodynamics, so I'm going to start by just reviewing, I guess summarizing it, not reviewing it. What it's all about is you have a physical system that you are describing with a continuous time Markov chain. You allow the rate matrix to vary in time. It's completely arbitrary. And so, for example, if what we're doing is having a discrete space of possible values x, that's continuous time Markov chain, it'll send a time zero initial distribution p0 to some ending distribution p1 at time 1. By the continuous time Markov chain, we'll actually be implementing this conditional distribution. So this is an extraordinarily general and broad set of systems that are described at least with very, very high accuracy by this kind of a model. Examples, particularly germane for the meeting today, this past week, is the noisy dynamics of a digital gate in a circuit. You could model with a CTMC, continuous time Markov chain, or for an entire. Okay, well, let's start to do just a little bit of algebra with this. So here's a formula. This is what is meant by continuous time Markov chains, the simplest possible thing. You've got a linear differential equation for the probability distribution of being in state I at time t. It is a stochastic rate matrix K, which we're allowing to vary with t, multiplied times your current distribution. Simple as you can be. Okay? Now for grins and giggles, let's just say you were bored one day and wanted to say, well, what would the time derivative of the Shannon entropy of my distribution be under a continuous time Markov chain? I've got nothing else to do with my afternoon. Let me calculate it. Well, it turns out that with just a half page or so of algebra, what you can do is you can decompose this into a sum of two terms, both of which depend upon the rate matrix K and the current distribution P. The first one is called in the literature the entropy flow rate. With malice aforethought, I'm writing it as Q dot because this is going to be related to entropy to heat flows out to your heat reservoirs when we use this to analyze thermodynamics. This other second term, which is being added to it, this is called the entropy production rate. This one, it turns out, is non-negative. You can actually prove that in only a few lines. That is crucial. In fact, that is what the modern understanding of the second law is basically this. So to unpack that statement of mine a little bit, so here we are, we're sending P0 of x to P1 of x. Here's our continuous time Markov chain. This is the decomposition of the time derivative of entropy. Let's just do the dumb, obvious thing. As I said, stochastic thermodynamics is gloriously simple. Time integrate this. Cool. You've now got yourself a formula for the change in the entropy of your system is equal to the negative entropy flow, which is the time integral of this, which is only a function of your initial distribution, by the way, plus the entropy production. So there are those terms being defined. Crucially, the time derivative of entropy production is non-negative, therefore the overall integral is non-negative. A great review article, by the way, I would highly recommend this. Christian Vandenbroek and Massimiliano Esposito. This one down here, you can read in a couple of hours. It'll be deriving all the stochastic thermodynamics I'm presenting today and a lot more as well. It's really great stuff. You can give it to your freshman class as just what some of the reading material for just a single week. Anyway, going back here, let's see what the consequences of this particular decomposition of the change in Shannon entropy are. Well, let's say that we've got now, that was all math. Now let's connect it up to physics. So let's say you've got a physical system that's connected to multiple reservoirs. For example, heat baths at different temperatures, like a heat engine. Note that because there's different heat baths, you can't even talk about KT. There's multiple T's, so there is no single KT. Let's allow an arbitrary number of states. Let's allow an arbitrary initial distribution, an arbitrary dynamics. Physics comes in by what's called a local detail balance, which basically means that you're assuming time reversible dynamics in your microscopic at the microscale. But in any case, once you assume this, then it turns out, it's easy to show, the entropy flow is the temperature normalized heat flow into the reservoirs. So that term is giving you your thermodynamic work. Okay, recall here our exact formula. This is not an inequality, this is an equality. Here's our exact formula for that heat flow into the reservoirs under this assumption. Well, remember that EP, we said before, is non-negative. The entropy production is non-negative. Therefore, the limit of this, when this thing equals 0, we get the heat flow into the reservoirs is going to be greater than or equal to the drop in entropies. This is now called the generalized Landauer's bound in the literature. Generalized because all of these things go far beyond what Rolf did about a half a century ago. So let's see exactly how it is extending what Rolf Landauer did. Simple example, let's say we're connected to a single heat bath at a particular temperature T, two possible states. It's a bit, let's just assume your initial distribution is uniform. This will turn out to be extremely consequential, by the way. And let's just say that, as everybody did back then, that you're only considering bit erasure. You're not even going to find bit erasure discussed in computer science theory textbooks. That's how sort of simple of a dynamics it is. So that means that your ending distribution is a delta function. Well, recall that what we're saying is the entropy flow is your initial entropy minus your ending entropy. That's the lower bound on it. If you're starting with a uniform distribution, that means your initial entropy is log 2. If you're ending with a delta function, your ending entropy is 0. In most forms of Pinot arithmetic, the difference between log 2 and 0 is log 2. Or actually, I guess that's beyond Pinot arithmetic, but never mind. Anyway, so therefore the generalized Landauer's bound in this particular case reduces to the one that we all know and love. The total heat flow from the system when this is your setup, is lower bounded by KT log 2. And there are a bunch of papers here that sort of go through all this generalized Landauer's principle. This one here I highly recommend to people. It unpacks our modern understanding of the relationship between logical reversibility and thermodynamic reversibility. They are different things, and we now understand the relationship much better than was done before by exploiting stochastic thermodynamics by Takahiro Sagawa. Anyway, so this is one example of the generalized Landauer's bound, or the decomposition of entropy flow that I gave right here. There are other ones. It turns out that you could entropy production, as I illustrated it back here, is a function of your initial distribution. And it turns out, in general, it can equal 0 only for a single initial distribution. I fixed my physical process so that it's got entropy production of 0 for one initial distribution. So I've got like a bit eraser that I'm using with one particular initial distribution that is optimized to be thermodynamically reversible for one initial distribution. In general, it will not be thermodynamically reversible if I run it for anything else. So if I'm, say, natural selection, I'm Darwin, I design a paramecium so that the environment that it's designed for of inputs from the outside world is thermodynamically reversible. You dump it into a different environment with a different distribution of inputs, it's not going to be thermodynamically reversible anymore. If I were to design my laptop so it's thermodynamically reversible for the initial distribution, a random distribution of inputs for me, then it would not be, in general, thermodynamically reversible if instead somebody else is using it besides me. And in particular, the formula for how your entropy production depends on your initial distribution It's the drop in KL divergences, what's called the contraction of KL divergence between your actual distribution and this idealized one for which entropy production would have been zero between the initial state of your system and the ending state. By the data processing inequality for KL divergence, we know that this is non-negative. So this is sometimes called the mismatch cost, because the mismatch between your assumption for what the initial distribution was of your environment when you designed your physical system compared to the actual one. So that has consequences. Let's now go back to our formula. Recall that the entropy flow is the sum of the drops of drop of entropy plus the entropy production. We just saw the entropy production was the change in the KL divergence. Add that change in KL divergences to the change in entropy, and what you get is your actual heat flow out to the reservoirs, is the drop in cross entropy, because that's what KL divergence subtracted from entropy is. Okay, what is the consequence of that? Let's say we're doing Landauer bit erasure. So the system is thermodynamically reversible, but let's say we know that, it's not an initial distribution of 50-50 of my bits. Because of where this bit eraser happens to be turning up in my system, what the environment I think it's facing, I'm going to design it so it's thermodynamically reversible for initial distribution that's, instead of being 50-50, it's epsilon 1 minus epsilon. So the minimal entropy flow, Landauer's bound. In other words, if you have zero entropy production for this thing, it goes to zero as epsilon goes to zero, as you become more and more sure what your initial distribution is. Now, though, let's say that, we happen to be using this bit eraser in a different environment where it's actually being used with initial distribution that's a delta function, about 1, rather than this Q0. Well, now your heat dissipation for this beast that was thermodynamically reversible, if you happen to get the environment right, in this other environment is actually infinitely larger than Landauer's bound. So even though you built this thing to be thermodynamically reversible, quasi-statically slow, all the rest of it, don't matter none. You put it in the wrong environment and you get screwed. So that's one example of a consequence of these results. Here's another one. Let's say that you have two distinct bit erasing gates. Heaven forbid, you've got a computer with more than one bit eraser. We're running them in parallel on bits XA and XB, and this is your initial distribution, your initial joint distribution over XA and XB. Assume that each gate by itself runs quasi-statically, slowly. Each one is thermodynamically reversible by itself, generates zero entropy production. Well, if this initial distribution actually statistically couples the initial state of your bits, then the full system is not thermodynamically reversible. Two gates, bit erasing gates that individually are thermodynamically reversible, you run them in parallel. In general, the resultant overall circuit, so to speak, is not thermodynamically reversible. What's going on intuitively is that there's information that you've left on the table, so to speak, when you run this parallel bit erasure. There, you have lost the information about the statistical coupling between the states of the gates, and that's why the overall system is not thermodynamically reversible, even though the two individual gates are. Okay, so those are some of the results I'll be pulling on. Here's another one from stochastic thermodynamics I'll be pulling on. This is so deep and profound, it overturns so much. But anyway, at the macroscopic scale, we all know entropy don't go down. It ain't possible. If I show you a movie of a macroscopic process, an egg falling off a table, you will be able to tell me if I'm showing you that movie running forwards or backwards. And we also know that at the microscopic scale, when you've got just elastic collisions between your idealized little teeny atoms, then the Liouville's theorem, entropy is exactly conserved. You can never tell on that scale if the movie of a given process is running backward or forward. Well, that was all well accepted all the way through to the beginning of the century, but there's an obvious question. What the blankety blank happens in between those two scales? You might expect that, for example, sometimes you can tell if the movie runs forward, sometimes you can't. What's going on? Well, this is one of the really cool things. So just reminding you, these are the formulas that I showed before. This is your continuous time Markov chain. The time derivative of the Shannon entropy breaks into the sum of these two terms. All of this is at the ensemble level. I'm averaging over many runs of my underlying stochastic process, of my continuous time Markov chain. There's averages over all of the possible states under the distribution defines all these things. It turns out that with stochastic thermodynamics, you can actually define these quantities at a trajectory level. So for example, what's called in the literature the stochastic entropy, it's minus log of pi. This entropy we're seeing up here is the average of that over pi's. But you can actually do all the thermodynamics, it turns out, at a trajectory level. So in particular, not only can you define entropy at a trajectory specific level, you can also define entropy production. Notice this is a sum over all possible states. You can define this instead where you're looking at only one particular transition. And when you do that, what you get are what are called the fluctuation theorems. People may have heard of like the Jarzynski equality or Kirchhoff's theorem or so on. What these tell you is that if we're looking at the trajectory level entropy production, so it's the average of this that I've been showing you before, it's the average of this that everybody had been paying attention to until the 21st century. If I'm instead looking at the trajectory level, you get this equation here, that the expected value over all trajectories of the exponential of minus kt times your entropy production, which is here being defined on a trajectory level, that equals 1. Use Jensen's inequality. What this is going to tell you, and this is our modern understanding of the second law, that the expected entropy production is non-negative. This is just as true microscopically as macroscopically. However, there is always non-zero probability that in any single sample of your process, you're going to have a negative value for entropy production. So what's going on at the mesoscale, the intermediate between the micro and the macro, is that you've basically got a probability distribution over your possible values of entropy production, which is now getting some non-significant mass at the negative values. Its average is never going to be negative. But as you go from the macro scale down to the micro scale, you'll be getting more and more probability mass over negative values of entropy production. And I should point out that all of this has been experimentally verified many, many times over. Many cover articles of Nature Physics, and so on. I'm demonstrating this in real physical systems. So I don't know. I just think that that is extraordinarily cool and deep and profound. It illustrates exactly how we go from the micro to the macro transition in the second law of thermodynamics. Okay, that was all really neat stuff. What has this got to do with computers? Well, let's start to do some of the most obvious things that we can with all the tools that I was just showing you. I assume everybody here knows what a Turing machine is, a universal Turing machine, a prefix universal Turing machine. And let's just start to see what the consequences are of stochastic thermodynamics. We use them to analyze Turing machines. Let's say that we've got a probability distribution over our inputs of the coin flipping distribution. This is the standard thing for algorithmic information theory, is all about assuming, in many, many ways, assuming that you've got a random process generating inputs to your universal Turing machine by flipping a coin. So the Kolmogorov complexity of a bit string, which you can view as the maximum probability of any bit string input S that would give you your output V if you're generating them according to the stochastic process, it's the minimal length of such a string, the maximum probability such an input string that would cause your given universal Turing machine to compute what the bit string is that you want it to compute and then halt. Okay, so as I mentioned, this is also the length of the most probable one. And so some people try to, I think, basically misuse this to say that they have a justification of Occam's razor, but that's a different talk. Okay, so, but let's now ask for a different question. The thermodynamic Kolmogorov complexity will be the bit string such that there's the minimal entropy flow for the Turing machine to compute V and then halt, give that particular input bit string. a very natural thing to consider. In fact, for computer engineers, this is arguably far more relevant than the standard Kolmogorov complexity. Well, what does that thing equal? Well, with a couple of pages of algebra, using all the machinery of stochastic thermodynamics, we can find that it is, so to speak, a correction to Kolmogorov complexity. Here's your bit string V, your output bit string. Here's its Kolmogorov complexity. Its thermodynamic Kolmogorov complexity is the normal one plus two terms. This term right here, it's like a partition function, log of it. It's a normalization constant, Chaitin's constant. This is Chaitin's omega right there. This thing here is actually sometimes called the universal probability measure in algorithmic information theory. It is the joint probability of any input string such that for one of those input strings, the Turing machine would actually compute that particular desired output string. This correction, what it's reflecting, is the fact that as the Turing machine evolves, it's undergoing many, many-to-one maps. Each one of those many-to-one maps is going to have a Landauer cost to it. That's essentially what all of this is capturing. What's the minimal number of amount of Landauer cost, cumulative Landauer cost, if you're just doing a Turing machine in the normal textbook sense of a Turing machine. So here's some of the really cool facts about that thermodynamic Kolmogorov complexity. Let's say very schematically, here's time of your Turing machine iterations. Here's your state space of the Turing machine. Here is your desired output string. Oops, go back. Here's your desired output string, and the Kolmogorov complexity is going to be the smallest input that would cause your Turing machine evolving through its state space to get there and halt. This famously is unbounded. There is no constant that exceeds this value for all possible v's. Guess what? Thermodynamic Kolmogorov complexity is bounded. There is a constant that exceeds the minimal heat dissipation to compute V for any possible desired output string. It's uncomputable, of course, but it exists. That's the first cool fact. Okay, so that means the minimal entropy flow for a fixed desired output bit string is bounded. Turns out, though, that if I just actually form inputs randomly using the coin flipping distribution of algorithmic information theory, so I'm making now many different outputs, the expected entropy flow is infinite. So for the minimal for any single specific input is bounded, but if I'm averaging over all inputs and therefore all outputs, now I get actually a value of entropy flow that's infinite. Okay, next on our list, we'll go on to the next one of the titans from the 20th century. That first was Turing, and now this, of course, is Claude Shannon. And who actually have a lot to do with the original work on actually circuits implementing Boolean functions, which is why he is gracing this slide. Of course, all computers today are implemented with circuits. The simplest one is one without any loops or branches. And so here's a schematic of such a thing. Okay, cool. Let's start thinking about what's the thermodynamics, non-equilibrium statistical physics, the stochastic thermodynamics of implementing such a beast, such a puppy. Well, recall this formula for our exact formula for the entropy flow out to the heat bath, drop of entropy plus entropy production. So also recall, actually this is everything to do with the input distribution. For a fixed conditional distribution, and that's what any fixed gate is. If I give you a gate, I'm giving you a distribution of its end states, giving its starting states. If I change the distribution over the starting states, I'm changing the minimal entropy flow. So this has got nothing to do with entropy production right now. If this gate is going to be thermodynamically reversible, if I change its initial distribution and then change the design of the gate so it's thermodynamically reversible for that new initial distribution, I change its Landauer cost, and so therefore I'm going to be changing the minimal amount of work that will require to run that gate. That's the first thing to notice. The second is if I take that fixed gate, put it somewhere else in the circuit, it's going to have a different initial distribution over its states. So therefore, if I optimize my gates, this is the most extreme thing you can imagine. optimize my physical gates for where they're going to end up in the circuit. So the same NAND gate, the same AND gate, different parts of the circuit, I'm going to implement with a different physical system just because there's different initial distributions, and I want to make sure that's thermodynamically reversible for the distribution at that point. So that means we've actually got ourselves a bit of an interesting calculation here. Even if each gate is itself thermodynamically reversible for the particular distribution of inputs it has, if I change this particular circuit diagram, even if it's implementing the exact same Boolean function, I'm going to be, for the same distribution over inputs, I'm going to be changing the accumulated Landauer cost. So we've got ourselves a design optimization problem. It's a expletive deleted design optimization problem, extremely rich, let's put it that way. To give a little bit of notation to just some of the simplest properties of this optimization problem, to remind people if they haven't come across it before, this quantity here, it's a generalization of mutual information, sometimes called multi-information, sometimes called total correlation. It's the entropy of a joint system, the sum of the marginals of the entropies of the marginals of a joint distribution minus the joint itself. It, loosely speaking, can be viewed as quantifying how much information is being shared among all those random variables. So, given that notation, here is something that you can derive. That if you've got a digital circuit with no loops and no branches, then if I go from one such circuit, C, to another one, C prime, the change in the total Landauer cost is given by the sum over all the gates of the multi-informations over the parents of all the terms in those gates for C prime and C. So what that's telling you is you should, the solution to your optimization problem, choose the circuit that implements your desired Boolean function with the smallest sum of multi-informations. Calculating that circuit is nasty, very nasty. Nobody knows how to do it. And even when you get to circuits that are only on this order of, say, half a dozen gates, it becomes very, very nasty to do this without just exhaustive search. And even with the exhaustive search, it's a pain in the ass kind of a calculation. Okay, so now the last thing I want to talk about is asynchronous computers. What I've talked about so far is just some of the ways that you can use stochastic thermodynamics to analyze the kinds of artificial synchronous computers that we all know and love. But even though we might love them, we're actually built out of asynchronous computers. Like here's an example. Charlie was talking this morning about the translation step of what's going on in genetic expression and gene expression. Here is it unpacked a little bit. This is actually an asynchronous process. All these things are going on simultaneously with their own random processes, and then they're communicating with one another by each of these processes by sending over some physical system, some physical substrate that's actually doing the communication. This fellow here, by the way, that's Carl Petrie of PetrieNet fame. So that's why I put him up next to these kinds of asynchronous networks. So, okay, cool. We've just looked at a little bit of what you can do for using stochastic thermodynamics for synchronous computers. What happens if we try to apply it to asynchronous computers? Well, let's go to a physicist's spherical approximation of a cow. Write down a very, very simple model of an asynchronous computer. So here is an asynchronous system. I've got 4 subsystems, 1, 2, 3, and 4. They're communicating with one another according to these red arrows. So here's their state at xt, at time t plus delta t. What these arrows indicate is that the state of subsystem 1 at time t plus delta t depends on its state at time t and the state of time of subsystem 2 at time t, but nobody else. Similarly, subsystem 2 depends on its own state and subsystem 3's state. Subsystem 3, though, note that it evolves autonomously. Its state at time t plus delta t is a function of its state at times t, but nobody else's. Okay, so this is kind of a generic example of it's an asynchronous system because all of these are influencing each other simultaneously according to the underlying continuous time Markov chain, which is actually generating these events indicated by these red arrows. So, for example, another way to look at it is that subsystem 2 is actually observing subsystem 3. Or, if you want to view it differently, subsystem 3 is actually controlling or helping to control subsystem 2. So notice that subsystems 4 and 2, they're not physically coupled. There's no arrows going from subsystem 2 to 4 or vice versa. But because they're all watching subsystem 3, or alternatively being controlled by subsystem 3, over time they become statistically coupled. So not surprisingly, there's a lot of rich information theoretic stuff going on in these kinds of things. Okay, so let's make a real simple definition. Let's say a unit is any set of these subsystems that evolves autonomously. So for example, remember I mentioned that subsystem 3 pays no attention to anybody else, and so therefore it is a unit. It evolves autonomously, only a single red arrow into it. Similarly, if you were to look at this pair of subsystems alpha, that pair evolves autonomously in the sense that there's no, their dynamics, that pair's dynamics has no dependence on anybody outside of 3 or 4. And my final example is this triplet is also a unit because this triplet of subsystems doesn't depend on subsystem 4. You can do whatever you want to subsystem 4. These 3 are just going to go along their merry way and pay no attention over there. So there's 3 units. Okay? So now remember from before that we can define stochastic thermodynamics at the trajectory level and recall the integral fluctuation theorem. This is how the second law goes from the micro scale to the macro scale. You're looking at the entropy production along a given trajectory. You're then saying that the average of that, of the exponential of that beast, for all trajectories equals 1. Okay, so kind of an obvious question. So this tells you about the fluctuations of entropy. That's why it's called a fluctuation theorem. For an integral fluctuation theorem, this expectation is an integral. And what's fluctuating is the amount of entropy production going over the trajectories. Well, we've got ourselves 3 units here. So an obvious question, you wouldn't expect, remember I mentioned that everything gets statistically coupled with time. So you'd expect each unit is fluctuating its entropy production by itself, but because of this kind of joint behavior, this governing behavior that they're all looking at, ooh, things got flipped. This is supposed to be indicating 3, and that's supposed to be indicating 4. My PowerPoint screwed up somewhere. But in any case, because of that, you might think that the entropy productions are actually become statistically coupled. So what that means is the amount of entropy being produced in this unit will depend upon the amount of entropy being produced in that unit in the organelles in your cells, for example. So let's see, it looks like I've got 5 minutes left. Let me try to go through this carefully. It's going to probably, I would expect I would lose most people here because there's a lot of stuff going down simultaneously, but recall that this integral fluctuation theorem, it only involves a single random variable. It's the entropy production that's fluctuating for a single system. We're now looking at multiple units, multiple groups of subsystems. Therefore, the associated formulas for the fluctuation theorems are going to be actually talking about how things are coupled. So here is one of them. Choose any unit. For example, it could be subsystem 3 here in the middle because that's its own unit. It turns out that the expected exponential of the entropy production that this puppy is making minus the entropy production of the entire system conditioned on that entropy production that this one's making, it equals 1. Every single organelle, set of organelles in every single cell in you is right now fluctuating how much entropy produces according to this kind of a weird formula. Okay, we can go a little bit further. It turns out that when you go down to the trajectory level thermodynamics, you can write the stochastic entropy production of the entire system as the difference of these 2 terms. This one is, so to speak, an inclusion-exclusion sum. So you're subtracting intersections, adding back triplets of intersections of the units, of the entropy productions of the individual units. This is actually a completely new information theory quantity. It's in essence an inclusion-exclusion sum of Shannon entropies. It can be viewed as a generalization of the multi-information, of the total correlation. So we can take this, we can plug it in there with these definitions, and I'll give you examples of this in a second. And what we get is this very strange formula once we apply Jensen's inequality. Having applied Jensen's inequality, the expected value of this inclusion-exclusion sum of the entropy productions in all the organelles minus this generalization of multi-information conditioned on the entropy production in just the central organelle is greater than or equal to that entropy production. It's a lower bound. So for example, plugging it all in for this particular case, here is the, frankly, very weird formula that you get at the end of the day, that the average value of the entropy production of these three subsystems, minus the entropy production of just this one, plus the entropy production of that one, minus, and here's the expected value of the change of Shannon entropy of your entire system, all of it conditioned on what the entropy production is over these two, is lower bounded by, this should actually have an expectation, the expected entropy production of those. So in any particular system, this is relating how the entropy productions of all your asynchronous units evolving simultaneously, of how the thermodynamics of all of them is actually being coupled through the topology of the underlying communication network indicated by these red arrows. So very, very strange stuff. What this actually means, nobody really knows yet. So in the last 2 minutes, I just want to make a plugs for some things. We had a workshop this past May on stochastic thermodynamics, where a lot of all this was on Zoom, out of Vienna. It was being hosted, and we're having another follow-on one for next May. Here is the page with information about the workshop that's being sort of put together as we speak, but it's live, so you can get information about that. Highly encourage everybody, of course, to at least participate, even if you don't want to present. There's going to be tutorials. It's very, very much designed to be a pedagogical thing. There's a wiki with all kinds of resources for the literature and so on. Here's its results. Here's a recent proceedings that touches on a bunch of these issues that came out last year. And here's a tome. This is a real big beast, but this one I put out last year. I was invited a review article on the stochastic thermodynamics of computation. And I've got a conclusion slide, but let me leave it up there so people can look at it and maybe take screenshots of this kind of stuff, because that's really the most important stuff. So, wow, with only 20 seconds to spare, I think I'm on time, and I'll end it there.
Thank you. Thank you.